All right, so now we are going to do the low temperature heat capacity. Now to do this, we're going to start with our constant volume heat capacity thing here. Now what we're going to do is convert this sum over k into an integral. And we can do this because we have so many k states to begin with. Like the number of k states equals the number of ions in the crystal. So we can convert the sum over k into an integral over a density. So this equals partial with respect to t. Keep the sum over s. Now, integrate h bar omega s of k and s of k. Now the density function is dk over 2 pi all cubed. Now, because we're at low temperature, we can approximate this omega s of k thing with something that looks like this. S of k equals the speed of sound in the k hat direction times the magnitude of k. So basically we have a linear dispersion curve. Okay, now let's make this look a bit more professional, let's say. So let's go down here. All right, so CV equals partial with respect to t, sum over s, integral of h bar. Substituting this thing into here, Cs k hat. Now remember what and s of k is. Times beta minus 1. So that comes to h bar cs of k hat. Because the speed of sound can vary with respect to which direction you're moving in. Times k times beta minus 1 dk over 2 pi cubed. All right, so now we're going to make the following substitutions. I can write those in a different color. All right, we're going to let x equal this thing right here. So, RCS of k hat k, which means dx equals h bar cs of k hat theta dk. And dk vector is k squared times dk and d big omega, because we're working in spherical coordinates. And also solving this thing for k, it means k as a function of x is x over theta. All right, so let's throw all this in here, shall we? See what we get. I'm going to start writing up here. So that is CV partial T sum of S. Integral, well, we get two integrals, one for k and one for omega. We've got a 1 over 2 pi cubed. The heck does this look? And if you look here, this thing is just x over beta. Yes. Okay, you got it. X over beta e to the x minus 1, which is the whole point of this. X minus 1 is dk because k d omega. And let's go with some more substitution. Get x squared. You get one of these things. Squared. Let's get it dx over another one of these things. Let's do 1 and d. And collecting some things. And separating things out. Now the only thing that depends on angle is this CS sort of thing. You get 1 over, and you have CS squared cubed, CS cubed, cubed. All right, that's the angle part. Now the x part. So you get x cubed x over x minus 1 and then your constants, which I could have taken out front, but I'm putting them at the back here. It's 1 over bar cubed 2 pi cubed and beta to the 4. You got 2 betas, 3 betas, 4 betas. All right, so what are the bounds on these integrals? So you can argue that this integral here goes from 0 to infinity in the low temperature limit. Now, if you actually change the bounds of integration during this step, you'll find that there's a dependence on beta when you change the variables. And because our beta is really high, you can say that we're integrating over this whole curve here. So there's this. All right, so let's look at this thing here. Let's put this in green. Now you could do the whole Taylor expansion thing, or there exists a formula to evaluate this thing. So the integral from 0 to infinity of x cubed dx over e to the x minus 1. This equals the gamma function of 4 times Riemann zeta of 4. Now you can look these up. You can look these up in the table of values. This thing equals 6. This thing is pi to the 4 over 90, which is just pi to the 4 over 15. All right, now looking at this thing, we can define the average inverse cube of the speed of sound as integral over like this. 1 over CSK hat cube d omega over 4 pi. Now this is just the average of the inverse speed of sound cubed. You can sort of see how we're integrating over the sphere, but we're normalizing it with this 4 pi here. All right, so now let's make some rearrangements here. Partial with respect to t, sum over s. Now I'm going to do some weird sort of things. It's going to break this up into 4 times pi times 2 times pi squared. Move this over to here. So we get integral over d omega over cs of k hat. That looks like a star there. Then we get this thing, plug it into here. Pi to the 4 over 15. Now the constants here. And because we move this here, we get 1 bar cubed, 2 pi squared, beta to the 4. Oh yeah, 1 over 4 pi. Now we see that this was our thing over here. This is partial with respect to t, sum over s, c cubed. Let's see, you got a pi squared on top, squared. 15 times 2 is 30. Bar cubed, beta to the 4. Now, let's apply the sum over s. Now, nothing depends on s, so, and we have 1 to 3 of these. Now, I'm also going to substitute beta as explicitly as function of temperature. This is 3 over 30 is partial with respect to t times 1 over c cubed pi squared 10 pi squared. Okay, Boltzmann t to the 4. Now we can take the partial derivative with respect to temperature. So this finally, Cv equals Boltzmann to 4 times 4t cubed and rearrange this a little bit, we get our final answer as 2/5 pi squared kb times pt over h bar c. That thing's all cubed. And there you have it. In the low temperature limit, the heat capacity is proportional to temperature cubed.